just days after Nvidia confirmed plans to open a dedicated research facility in Shanghai. An unmistakable response to intensifying U.S. export restrictions on its most advanced AI accelerators. And on the eve of Xiaomi's surprise unveiling of its first in-house mobile processor, the Zring01, China's semiconductor drive has entered a high-stakes new chapter. Over the last 10 years, China has marshaled state coffers, industrial policy, and human capital in an all-out push to challenge the global semiconductor hierarchy. Semiconductors, the microscopic engines powering everything from everyday smartphones to hyperscale data centers and frontier-class AI inference systems, have traditionally been controlled by Intel, AMD, and Qualcomm in the x86 and mobile CPU markets, and by ASML's extreme ultraviolet lithography machines in advanced fabs. Yet China, now responsible for more than 50% of worldwide chip consumption and spending approximately $450 billion on imports last year, nearly double its annual oil import bill, has cast semiconductor self-sufficiency as a matter of national security and economic destiny. Beijing first signaled its ambitions with Made in China 2025, setting an initial goal of replacing 70% of imported chips with homegrown versions by 2025, followed by a vow to eradicate all foreign dependency by 2030. Successive 5-year plans have reinforced these targets, while parallel initiatives like the National Chip Implementation Plan, launched in 2021, have added detailed roadmaps for everything from talent development to test and measurement equipment. To date, the government has funneled well over $60 billion into direct subsidies, preferential loans, and tax rebates, catalyzing the rapid registration of more than 28,000 semiconductor companies, an increase of nearly 270% since 2020, and swelling a domestic workforce that now exceeds 600,000 engineers, designers, and fab technicians. Central to this mobilization has been the National Integrated Circuit Industry Investment Fund, widely known as the Big Fund. Since its 2014 inception, 3 major tranches, Yen 139 billion in Phase 1, 204 billion yen in Phase 2 and 344 billion yen in Phase 3, approved in May 2024, have underpinned wafer fab expansions, specialty chemicals manufacturing, and equipment R&D. A fourth infusion, projected to exceed 400 billion yen, is slated for later this year. These state-backed resources are routed through public banks and sovereign wealth vehicles, effectively underwriting an end-to-end domestic supply chain that spans silicon wafers, photomasks, lithography systems, and even the ultra-purified gases and photoresists once monopolized by Western suppliers. Despite aggressive capital deployment, one gap has stubbornly resisted closure: access to EUV lithography tools, ASML's crown jewel machines needed for sub-7 nm processes. U.S. export curbs have blocked Beijing's path, so Shanghai Microelectronics Equipment stepped into the breach. In late 2023, SMIC premiered China's first deep ultraviolet stepper capable of 28 nanometers production, unlocking mid-range nodes critical to 5G base stations, automotive microcontrollers, and industrial IoT. Alongside parallel efforts in homegrown EUV light sources, insiders at SMIC hint that a functional prototype could emerge by 2026. An achievement that, if realized, would slash China's reliance on foreign machinery and reshape the economics of advanced node fabs. Remarkably, even without full EUV access, China has notched headline-making advances. In mid-2023, SMIC commenced volume production of a 7 nanometers mobile processor, the Kirin 9000S, designed by Huawei's HiSilicon unit and powering the flagship Mate 60 Pro. Manufactured via an enhanced DUV multi-patterning process, this chip delivered benchmarks comparable to Qualcomm's 5 nanometer Snapdragon series, proving that, through relentless process optimization and alternative lithography flows, China can bridge a 2-generation technology gap despite sanction-induced constraints. Yet industrial policy alone cannot secure long-term autonomy. Control over processor architectures and design IP is equally critical. To sever dependence on Intel's proprietary x86 cores and ARM's UK-based licensing model, Beijing has thrown its weight behind RISC-V, an open-source instruction set architecture immune to Western licensing fees. In early 2025, the Ministry of Industry and Information Technology issued guidelines compelling at least 8 state agencies to adopt RISC-V in new procurements spanning edge computing platforms, IoT devices, and data center servers. Simultaneously, homegrown designs like Lungsun's Long Arch, a 64-bit architecture seated in government laptops and high-performance embedded controllers, are gaining traction, signaling a multi-pronged approach to architectural independence. Software is equally vital. Until recently, electronic design automation tools for chip layout and verification were dominated by U.S. firms such as Cadence, Synopsys, and Mentor Graphics. In response, a consortium led by the China Electronics Corporation, Alibaba Cloud, and Tencent Cloud has developed 78 domestic EDA tools covering the full design flow for 14 nanometers and above. From RTL synthesis and place en route to DRC/LVS verification. These tools are now in commercial use at major design houses, from startup fabless companies to research institutes, effectively closing the gap on critical software IP. None of this progress would be possible without talent. Over the past 5 years, China has aggressively recruited experienced engineers from Taiwan, offering equity packages and R&D grants, and enticed overseas returnees with entrepreneurship incentives and research stipends. At the same time, universities have ramped up semiconductor curricula. The total number of undergraduates and graduate students in microelectronics programs has more than tripled since 2018, reaching over 40,000 enrolled in 2024. National scholarship programs now funnel thousands of top math and physics graduates each year into semiconductor research. While partnerships with European and Singaporean technical institutes provide cross-border training and joint lab opportunities, Huawei occupies a central role in this ecosystem. Once the target of sweeping U.S. sanctions, it has become a powerhouse of chip innovation. Beyond HiSilicon's processor cores, Huawei invests heavily in its Ascend series of AI accelerators, some capable of 1,000 tera operations per second, and in advanced 3D chip stacking and packaging techniques that boost performance and energy efficiency. By integrating RISC-V cores into smartphone SoCs and backing multiple EDA tool ventures, Huawei helps bind together a domestic supply chain that now extends from silicon foundries through software stacks to final assembly. China's semiconductor reach now extends far beyond its borders. Under the Belt and Road Initiative, Chinese equipment makers, design centers, and training academies have established presences in Southeast Asia, the Middle East, and Eastern Europe. Localized R&D hubs in Malaysia and Poland, staffed by Chinese and international engineers, serve as testbeds for new chip designs and manufacturing processes. These partnerships not only diversify market dependencies but also provide crucial feedback loops that accelerate iterative development. The impact on global supply chains is already palpable. In 2024, China accounted for roughly 40% of all spending on chip manufacturing equipment worldwide, absorbing every export-permitted machine and submerging mature node capacity. Moreover, China's share of 7 nanometers wafer starts jumped from under 5% in 2021 to nearly 20% by the end of 2024, thanks to multi-patterning improvements that have brought yield rates within 90% of those at TSMC and Samsung. Low to mid-range chips, those nodes that power everyday electronics such as set-top boxes, vehicle controllers, and 4G per 5G handsets, are now produced almost entirely onshore, insulating China from future supply shocks. Looking ahead, if Beijing maintains its current pace of funding and technical breakthroughs, indigenous EUV or EUV equivalent machines could enter pilot production by 2027. That milestone would unlock genuine high-volume manufacturing at 5 nanometers and below, positioning Chinese foundries to serve the most demanding AI, high-performance computing, and advanced mobile markets without foreign assistance. Even with the inevitable challenges of achieving world-class yields, securing specialty gas supply chains, and navigating further geopolitical headwinds, the sheer scale of China's industrial mobilization makes it one of the most formidable semiconductor efforts in history. When a nation combines unwavering political will with deep financial reserves and a rapidly expanding talent pool, its odds of technological success multiply dramatically. By 2030, the Silicon Dragon may transform from a global assembler of chips into a genuine superpower, capable of competing head-to-head with the world's most advanced fabs and redefining the balance of technological leadership in the digital age. As multinational incumbents adapt and new challengers emerge, the world will watch China's semiconductor odyssey with profound strategic interest, and, as always, we'll keep you informed.